What's up guys, Noah here with a little video on photon momentum applications. Quick overview of what we'll be talking about. A photon is a particle of light, momentum is oomph, and photon momentum is a new concept and is calculated by dividing Planck's constant by the wavelength. If you remember, h represents Planck's constant, 6.626 times 10 to the negative 34th, and lambda represents the wavelength. P is the variable that represents momentum. So if you type photon into Google, this is what you're going to get. A particle representing a quantum of light. And a quantum is just like a little package. And a little history quiz. Who discovered the photon? Who had this big idea, I guess? Nikola Tesla, Albert Einstein's Angelic Zeroger, or Richard, that should say Max Planck. And if you guessed Einstein, you're kind of right, because he was the guy who theorized that it was a thing, but it was actually this man right here, Arthur Compton, who received the Nobel Prize in Physics for discovering the Compton effect, who experimentally observed the photon first. And the Compton effect pretty much shows what he did was he shot photons at an electron, and it would actually give them some kinetic energy. So he was able to show that photons really do exist by displaying their momentum. So you see here the photon has velocity, bumps that electron and gives it some energy. And we'll be talking more about the implications of photon momentum and why it's important in our everyday lives as well as intergalactic space travel. So the photon wasn't necessarily discovered but theorized by Einstein. And a photon is interesting because it doesn't have any mass. And its energy is proportional to the frequency of the electromagnetic radiation. So we've all seen in other science classes, maybe other physics classes, this right here, the electromagnetic spectrum, that's pretty important. So we need to remember that light doesn't just reside in the visible spectrum, but it's there are a lot of forms of light and a lot of energy levels of that light. So momentum, let's brush up on that real quick. Momentum is the oomph, and this is a big deal in Newtonian physics, right? If you think about a big truck hitting a traffic cone, that truck has a really large mass, and it's going fast too. So it has a really large velocity. You can imagine that it's going to have a lot of momentum to it. So the easiest definition of momentum is that it's oomph. So now let's get to the good stuff. What is photon momentum? When we combine these two ideas, what kind of implications does it carry? Well, as we know, photons behave really weird because when you're traveling at the speed of light, Newtonian physics doesn't really hold up as well. So the new equation for calculating photon momentum is this. The momentum is equal to Planck's constant divided by the wavelength of the photon, of that light. And you may be wondering, is this on our equation sheet? It is. I went and found it for us. Can make things easier. It's on the second page right there. And it's really applicable for problems like this and all of the figures and pictures in my slideshow come from the OpenStax textbook. But this is really a good one. It says calculate the momentum of a visible photon that has a wavelength of 500 nanometers. So 500 nanometers is 500 times 10 to the 9 meters. And we're going to put that under 6.626. And the book actually uses 6.63 times 10 to the negative 34th, and that's joules per second. And it's going to give us our momentum, which is equal to 1.33 times 10 to the negative 27 kilogram times meter per second. So this is cool because the second part, B, says find the velocity of an electron having the same momentum. So now we see how the photon momentum can be related to a more Newtonian view of momentum. And so here P is going to be equal in both scenarios. So here the momentum is 1.33 times 10 to the negative 27. For the electron, the momentum is going to be the same, but to find the velocity that the electron is traveling, we're going to plug it into P equals mv, and we're going to use the mass of an electron to get there. So the mass, there we have our momentum, and we're going to rearrange our equation so we have the velocity is equal to the momentum over the mass. And so we'll divide it by the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. and that'll get us our velocity, which is 1,460 meters per second. So it's super useful, and we'll definitely be seeing this on homework problems in the future. Okay, now let's get to some photon momentum applications. So here are three major ones that are brought up in the OpenStax textbook. And first we have comet tails, solar sails, and then optics. So that's any kind of imaging device, cameras, eyes, things like that. And so let's get into comets first. So Halley's Comet. We've all heard of Halley's Comet. Have you ever thought about why it has this big tail? And I mean, when we picture comets, they have these enormous tails behind them. And so why do you think they have those tails? What do you think? If you picked B, you're wrong. If you picked A, that's always what I thought. But it's not that it's burning up in the atmosphere, because interestingly enough, Halley's Comet is super far away. The closest it's ever been was 3.2 million miles away. So it's not even close to the Earth's atmosphere. The comet behind it, the tail behind the comet is actually from photon momentum. So photons from the sun hit the comet and blast off these little pieces that fly behind it. And so let's look at another picture of it here. If you have a comet traveling and orbiting the sun, the tail is always going to face away from the sun, because photons from the sun are going to be hitting that comet and knocking little particles off, because these photons carry so much momentum. So the answer is C. It's photon momentum that's causing this phenomenon. So this was discovered, interestingly enough, because if we were to be observing, let's say this is Earth right here, that little circle, that's us, and we're observing this comet fly past us, we would expect the tail to be going away from its velocity. That makes sense in a classical setting. But if we were on the opposite side, and let's say the comet's flying past us, but the tail is going in the opposite, or going in the same direction, that's the inverse of what intuition would say or classical physics would say. So the answer to this is that the tail is always pointing away from the sun. So here I've highlighted, these are like photons, let's say, that are like being emitted from the sun, and these are going to hit the comet and blast little things off. So the tail is always facing away. And this has led to some seriously interesting advancements in space travel. So this right here is this is like concept art for something called a solar sail. And these have actually been launched, and the US is planning on launching one in this decade. But what these are these massive and super lightweight sails, and they function similarly to the comets or sails on a ship, and they point in the direction that they want to be carried, and then the photons hit them and propel them forward. And so you can think of these photons coming in and hitting this thing that's carrying a payload, and it's just a really efficient way to travel through space. You don't need a ton of fuel. You're just relying on energy that is already all around, at least in this solar system. Here's another picture, so we can see the payload there. Let's say the sun is this highlighted blob, and photons would hit it, and then the solar sail would be propelled in that direction. Here's actually an actual solar sail that's being built, and this is the US version. It's called the Light Sail 1. This is from OpenStax, figure 29.19, and it has a 40 square meter sail. So if you look at those little people down there, I mean, this thing is huge, and it's going to be sent into space sometime in this decade. So then let's get into the last application I wanted to highlight, which is eyes and optical devices. This is a really concise summary of what's going on here that I recommend you check out in the OpenStax textbook. It says almost all detection systems talked about thus far: eyes, photographic lens plates, photomultiplier tubes and microscopes, and CCD cameras rely on particle-like properties of photons interacting with a sensitive area. So photons carry this momentum, and they can interact with either like a digital sensor or something more analog or something biological. So if we were to look at this light coming through an eye, light coming through an eye. On the bottom here we have the retina, and there are these photosensitive cells that will actually change their conformation when they interact with photons, and it's very important in biology how these photons have momentum. They interact with the world around them, and we wouldn't be able to perceive light if it weren't for the fact that light existed in this wave particle duality, and it carried momentum like it does. And so there have been a lot of really wonderful discoveries along this, and I hope that this video helped you better understand why these are so important. And here's a little summary. So photons have a wave particle duality. Momentum is oomph, and in classical physics, momentum is equal to mass times velocity, and photon momentum P can be calculated by dividing Planck's constant by the wavelength. And the applications we went over were, again, comet tails, solar sails, and vision and imaging devices. Thank you very much.